Welcome to video 6.5 periodic trends. So we're going to talk about a couple of different trends, and when I say trends I mean going across the periodic table and generally what happens as you go across or down the periodic table. So the first periodic trend is going to be atomic size or atomic radii. So atomic size is a periodic trend influenced by electron configuration. Think about size. What you're generally going to think is as you get more electrons, the atom is going to get bigger. However, that doesn't always work. For metals, remember, you're always going to measure radius as half the distance between the adjacent nuclei, or basically the distance from the nucleus to the outside of the electron configuration, or the valence electrons. So it's half the distance between nuclei of identical atoms. So look right here, this would be your atomic radius, or this would be it. So you can measure from nucleus to nucleus, or nuclei to nuclei. It's really easier to go nuclei to nuclei, or nucleus to nucleus, because then you can just divide it in half. We don't have a specific dividing line. Oh, here is where the electron cloud stops. So the trend in atomic radii is as you go from left to right on the periodic table. So I start at helium and I go over to, I start at hydrogen, I go over to helium. I start at lithium, go to beryllium, go to boron, go to carbon, go to nitrogen, go to oxygen, go to fluorine, go to neon. It's as you go across the periodic table, and this is weird, you're adding electrons, but the radius gets smaller. Wait, what? Why? Because you're adding more protons and more neutrons, and more electrons and more neutrons. But as you add more protons and more electrons on that same energy level, so going from left to right on the same energy level, the radius is going to decrease because you're increasing the positive charge. So as they're not shielded from that increasing nuclear charge because there's no additional electrons between the nucleus and the valence electrons. So like I said, if you're on that same energy level, it's going to just get smaller. It's going to kind of collapse in on itself. So that's called the shielding effect, is that inner level electrons block the attraction of outer level electrons to the nucleus. So as you go across the periodic table, the atomic radius is going to decrease. But as you go down the periodic table, the atomic radius is going to increase because you're adding more electrons, but you've also got more shields because you're adding onto a new energy level. So that is why as you go down the periodic table, the atomic radius increases because you are adding more protons and new electrons into a higher energy level. So it increases as you move down the group because you are adding energy level and the orbital size gets bigger. So let's look carbon, fluorine, beryllium, or lithium. Which has the largest atomic radius? So what I'm going to do is I'm going to find all of those on the periodic table. And I find carbon is number 6 in group 14. Fluorine has an atomic number of 9. It's in group 17. Beryllium has an atomic number of 4 and it's in group 2. And lithium has an atomic number of 3 and it's in group 1. All of those are on period 2. So which one has the largest atomic radius? It's going to be lithium because it is on the left side of the periodic table. Beryllium would be next. Carbon would be the third largest, and fluorine would be the fourth largest, or the smallest, because you're adding electrons to that same energy level. Alright, our next periodic trend is ionization energy. And ionization energy is defined as the energy required to remove an electron from a gaseous atom. And next chapter we'll talk about what an ion is, but it's removing an electron. So, ionization energy is how much energy it takes to make an ion. So the energy required to remove the first electron is called the first ionization energy. So when we remove that first electron, and that's the first ionization energy, it's going to be like, okay, how hard do I have to work to get an electron off of this atom? So if you look at this, you'll notice, looking at the graph, that ionization energy increases most of the time as you go across the periodic table. Although it's kind of a little jagged, it always starts going up, then down a little bit, then goes back up, then down a little bit, then goes back up. And you notice that trend on each of the periods. So you've got period 1 over here, period 2, period 3, period 4, period 5. This is because the first ionization energy increases from left to right. So this is the opposite of the atomic energy. So it's going to increase because the atomic radius. Because the atomic radius decreased, it's harder, so you have to use more energy to get one of those electrons out. So, as you go from left to right across the periodic table, as that atom gets smaller, you have to use more energy to make it into an ion. As you go down the group, the ionization energy would decrease. Because that atom is because that atom is bigger, and because its electrons are shielded from the nucleus as you add more energy levels, it's easier to steal an electron. So your ionization energy is going to decrease as you move down the group. So this is the trend in ionization energies. When you remove a second electron, that's called the second ionization energy. It requires more energy. And each time you ionize something, it's going to require more energy, though it's not a linear increase. Ionization, when you have the largest increase in energy, that's related to the valence electrons. Then there's also something called electronegativity. And electronegativity is similar but not quite the same as ionization energy. Ionization energy is how much energy it takes to remove an electron from that atom. Electronegativity is the ability of that atom to attract an electron. And that's going to be important. It's how it attracts electrons, which is why it's called electronegativity, because it's negative. And it decreases down the group and increases left to right across the period. So it looks kind of like this. It's going to follow the same trend as ionization energy. A good rule of thumb is actually just the closer to fluorine it is, the more electronegative it is. Also, if you look on your periodic table, you have electronegativity values in the bottom right-hand corner of every element block. So whatever has a higher electronegativity is going to have a higher electronegativity. So if it's closer to fluorine, it's going to be more electronegative. Thanks so much, and we are done with Chapter 6.